So, good morning and welcome back to Scientific Visualization. Today's topic, dense flow visualization. So, I talked about flow visualization a little bit, about glyphs, for example, drawing arrows, drawing a bunch of arrows to show flow direction to indicate the flow. And then I talked about methods for computing particle traces. And then we can use these particles or the points, the positions of these particles that we follow through the flow. We can use those to connect them, for instance, as a line, to connect them as a tube or a ribbon or various other methods or various other visualization outputs, so to say. Okay? So we had glyphs so far, and we had these what are called integral curves. You also learned that there's 4 different types of curves. There's streamlines, streak lines, path lines, and timelines. And some of those can be combined. For instance, you can combine timelines with streak lines to get what's called streak surfaces. What all these methods had in common, though, was you had to choose specific points where to start a line or where to place a glyph. And that choice can be good or can be bad. So if you pick a place where nothing is going on and you don't pick a place where like the important flow property is visible or would be visible, then, well, you miss it. And that's usually a bad thing. If there's too much input into the visualization that can be, well, that can be faulty, then there's a potential source of error. Dense flow visualization, on the other hand, is a method that gives you a complete view of the entire flow field without any choice to make. So this image that you see here, for instance, of a flow field was pretty much computed without any parameter at all. So you just throw in a flow field and you let it go. At least the method itself has a couple of parameters, but none of those are things that you usually need to tune if you implement it right. So that said, we're obviously here relatively far at the bottom in our visualization pipeline, so we are concerned with mapping and then ultimately rendering, whereas in the case of dense flow visualization, the rendering is usually fairly trivial because it's either going to be just an image that you just display in an image viewer or you write out, or in case of volumes, it's something that we've talked about before. Okay. So there's a number of methods for this dense flow visualization for generating images that are, well, dense, that don't require specific starting points or anything. But the most popular one is certainly LIC, line integral convolution, and variations thereof. So I'll focus my talk here on LIC, but be aware that there's other methods that achieve similar results, but they are by far less popular. Okay, so here are a couple of examples of LIC images. And the nice thing about LIC is that it can really be explained easily in I would say probably 3 minutes, at least the basic technique. And then there's a couple of things to know on top of that to get the images to work well. But the basic idea is really super simple. You start with usually some sort of random input, just noise on the left. And then to create an image such as this one here, so this is a flow around a Porsche, I guess. To create an image such as this one here from the image on the left, all you do is you smear this texture here along the flow. So imagine that this is sort of paint drops, right? White and black paint drops. And what you do is for each pixel or for any like part of the final image, you put a finger down and then you move that finger around and smear the paint, the wet paint along that path. So that's pretty much the idea behind the method, except that there's no finger or paint involved. Okay, so that's the overall idea. And then why does it work? Why do we get a dense flow visualization with that approach? I mean, well, the implementation looks a little bit different than using a finger, but that's really what we do. So why does it work? Why do we get an image that we can interpret relatively intuitively? And that's what you see here is a super complicated flow field, right? It's a flow field that has a bunch of vertices, has well, all those critical points here. And so it's not just a simple flow around a cylinder or something that we had before. It's something that's very chaotic. So why can't we still interpret that? And the overall idea is that if you take that random input and you smear it along a path, what happens along that path? Well, along that path, you get some sort of correlation, right? I mean, that's what smearing really means. You take part of the ink or paint along your path and you combine it with other parts of that path. So you get some sort of correlation. So you get like an average color, so to say. I mean, it will vary along the path, right? So if you have a white spot, that white is smeared along the path and you move maybe into a dark region and then it sort of gets dark, but there's some sort of correlation. Whereas if you choose your noise properly, I mean, like really uncorrelated noise values, then across the flow, right, there shouldn't be any correlation at all, right? You just compute the average over some values here and average over some values here, but they should be pretty unrelated. So that's the overall idea, that we have a uniform or similar structure along the flow, and across let's say streamlines that we compute, we don't have this structure. So, and humans, I mentioned this a couple of times throughout the lectures, we're immensely good at finding lines, finding structures, identifying those, following them. And that's what we make use here in these images. Well, now so much for a very abstract view. How is this whole smearing process implemented? And that's not even very hard. It's actually very simple when we have when we combine the ideas that I presented before. Okay? So here's a broad overview of how the method works. So what we start with is obviously a vector field, and let's just assume we have a 2D vector field for now. So what we start with is a vector field on top here, and we start with some input texture that is usually noise. Again, you can choose other things, and I'll give you a few examples later on, but it's usually uncorrelated random numbers in a two-dimensional grid. Okay, so, and another simplifying assumption here is that everything has the same resolution. So we assume that our output image has the same resolution as our vector field, has the same resolution as our noise texture. And the noise texture we can turn into any resolution, and the vector field, for instance, we can give this the same resolution as the vector field. And we can also render it in the same resolution as output. So that's not really a big simplification. So let's say we have a 100 by 100 pixels vector field. That means we get a 100 by 100 pixel noise image, and our output image should also be 100 by 100 pixels. So the next thing we do is we compute each and every pixel completely independent. Okay, so each and every pixel is considered as one entity. We run a computation on that one and proceed to the next one. Okay, so that said, we'll focus on one single pixel here. And the one that I've chosen can be seen here at the top. So that's the base of the arrow. So that's pretty much this pixel here. Let's say I want to compute this pixel. So now what I can do is I can take that one pixel and I pick this as a starting point for a streamline. Okay, remember streamlines. I've explained those in the last stream. Interesting. So if you're unfamiliar with streamlines, you can go back and review the last stream. Okay? So that streamline then creates a line in the flow, which happens to be straight here. Okay, but of course a streamline is usually a curvy thing. Okay, so don't be fooled by this straight line here. So I've just drawn this as a straight line, but it's effectively a particle trace through the vector field that is frozen in time. Okay, so that would give me, for a vector that points in this direction, something that wiggles here this way. And I also compute the streamline in the opposite direction, which is fairly straightforward. I just have to choose a negative delta t, okay, or a negative delta u. So my parameter that I use to multiply the vector field, if I simply make this negative, all the vectors will flip, so I get this part here. So what I've done for that single pixel only, I've computed the streamline that moves or that passes through that pixel. Okay? Why do I say that streamline? Because there's only one streamline that passes, if I point sample, say the center of that pixel, at any point in a space, there can only be one streamline. Okay? And I don't have to consider time because streamlines don't consider time. Right? Remember, streamlines don't cross. So there's only one streamline that goes through, and this one I compute here. Okay, now what is a streamline? A streamline is effectively the way we compute it. It's a set of points, right? It's just a set of points that we connect to a line. And all we care about here is the set of points. We never really draw that line. What we do is we take all of these points here along the line that we computed. And again, it doesn't have to be straight, right? It usually isn't straight. So all of those points, we now project them into the noise texture, which effectively means just take their coordinates and check this in, check up that point in the noise texture. So what I get then is from a single pixel, I computed a set of points, and from that set of points, I now have a set of noise values. So a set of, if those are random numbers between 0 and 1, so I just get a set of values between 0 and 1. Right? They don't have to be 0 or 1, they're usually something in between. So that's then my first result from Lick. Now, how do I combine all of those values into just a single pixel value? Right? I mean, that's what I want to do. I ultimately want to write out a single pixel value. Well, then all I have to do is compute a weighted average. I could also just compute an average for simplicity's sake. I could say, well, I take all of those values here, which are values between 0 and 1, and I compute the average and I get out, what, I don't know, 0.6 or so. So I write 0.6 into that pixel, and I'm done with that pixel and proceed with the next one. And since they don't talk to each other, I can also run this in parallel if I want to. Okay, so that is the overall idea of Lick. That's pretty much it. Any questions so far? Okay. And then let's look at some of the details of this method. So here is the 2D Lick formula, and it also explains a little bit why this is called line integral convolution. Okay, so where's the line, where's the integral, and where's the convolution? Well, the line is the streamline that we compute. Okay, and again, it's not straight, it's just line. This might be a little bit misleading here. So what's the next thing? Wait a second. Okay, so got this sorted out. So what's the convolution that we do? Well, I said we compute those points, right? We compute the set of points, I don't know, maybe 100 points in the future and 100 points in the past. So we get this 200 point long line. And now I said we can compute the average over this line. Yes, it's perfectly valid. And when you do the exercises, you can also take the code that we give you and you can actually implement it with average and you can check what happens. It'll actually sort of work. But in the more general setup, you can also, okay, instead of computing the average over all values uniformly, we can compute a weighted average where we consider the value at the center with a higher parameter, and then we have some sort of decay into those two branches. Okay, so that means we apply some sort of filter, for instance, a Gaussian filter, very popular here, a Gaussian filter that weights values in the center higher than the values towards the beginning and the end of that streamline. Now, that's the first thing. So we have to multiply it with a kernel then. That's this k here. This is our weighting function. And that kernel could just be a constant, right? It's perfectly fine. So that would mean do an average. And then ultimately, we sum all those values up. So that's where the integral comes in. Okay, first line computation, then multiplication with the filter. That's the convolution. And ultimately, integration is summing the values up. Okay, so still nothing really hard about this method. And well, there won't be anything super complicated here. So it is a pretty simple method by itself. That's still immensely powerful if used correctly. So that's this is really a big deal. So here's just an example for a kernel. I said you can use a box filter, so you just have a constant, but Gaussian filters are the most popular choice. Why is that the case? Well, if you think about the fact that we compute each and every pixel separately, right? There's this question, why would that result in a consistent image if I compute each and every pixel independently and don't consider any of the neighboring pixels in the process? How can that computation lead to a overall image that, well, results in consistent structures? And the idea is that if you have one pixel and you start your streamline, it'll go through other pixels. Now, if in one of those other pixels I start a streamline, I'll most likely get a very similar streamline, right? Since the one streamline doesn't have to pass through the center, it's probably not exactly the same, but I'll get a pretty similar one that has a significant overlap with the previous streamline that I talked about. Since they have a significant overlap, they access the same values, they average the same values, so the color, the output will also be very similar, and that's where you get your correlation from. Now, when you shift your stream, when you think about shifting your kernel along one of those streamlines for a second, then you get new values. Say I do 100 values in one direction and 100 values in the other direction. You lose a couple of values and you gain a few ones, right? And you want those to like slowly fade in instead of just giving them full access the moment I touch one or I lose one, okay? And that's the reason why it sort of makes sense to have this filter that slowly weights values more towards the center, and then they lose weight, okay? So normally we choose this normalized, okay? So we want the overall values. When you sum this all up, we want the overall value sum to be somewhere between 0, 1 again, and we want this to be symmetric. So there's hardly any reason why this filter should weight values in one direction other than the other direction, at least not for now. Okay, and then all you have to do is, well, you combine all these things into one consistent image. Okay, input noise, vector field goes into this convolution process after the computation of a streamline, and then ultimately we get, well, this final Lick image out. And here's a few more examples. So on the left, there's a typical two-dimensional Lick image. You can also apply this to surfaces. More on that in a few minutes. Okay, so the process is very similar to the planar process. But let me first talk about other things that we could do. For instance, we don't have to choose noise as input. We can choose whatever we want. For instance, we can choose a picture. Okay, so we can take a picture here, and we can choose that picture as input. Well, then it probably makes sense to use some sort of vector field that is related to the picture. And for instance, we can use the gradient image. If we take that picture and we compute the color gradient, okay, which is a vector, and we use that as the vector field, then we end up not really doing vector field visualization, but we end up with an image filter. So that's maybe like a liquify filter or whatever we could call that, right? And it kind of makes sense because what it does is it would smear the image in the direction of maximum change, which is really assuming that this is thick paint and it kind of flows on a canvas. And which direction would something flow? Well, it flows into the direction of the maximum gradient, right? So way down, so to say. So you can also use Lick as a filter for images, as an artistic filter, and it's certainly integrated into any imaging software these days. So it's not just a visualization tool. As a matter of fact, actually, when Lick was proposed, so those were actually images from the original publication. It was used as an image filter. So here's another example. In this image, you see Boris Yeltsin holding his hand, and he's certainly waving, but that doesn't show in this short exposure image. But if we want to apply motion blur, we could, for instance, use Lick by just running this image, using this image as input, using a vector field that is stationary, that is a 0 everywhere, except for those few points at the hands where we introduce some vectors, and then this would get blurred. Okay. Obviously, it's a very simple blurring filter that has a few issues. So for instance, the camera here is also blurred and parts on the other side would also be blurred. But nonetheless, it works very, it's a very nice quick shot. It works reasonably and it's very easy to compute. Okay? I just wanted to mention that a lot of the things that we do in visualization also have maybe even origins, but they also have applications in other fields. Okay? And this is what happens if you input something other than noise. If you input very structured images, you will, well, get those out depending on how much of a vector field you throw at them. So here's another example, now back to visualization. Classical example, wind fields, in this case over North America, but you also see lick images these days in weather forecasts in Germany. So when you check out the weather forecast, every channel does it a little bit differently. But in the old days, when I was little, glyphs were the primary visualization technique for weather forecast to the masses. And now lick images are also used. So it seems like they've made their way into mainstream visualization. Okay, so that's another application. Here's yet another use of dense flow visualization. And what I want to show here is that lick generally produces a black and white image or a grayscale image, right? If you throw in a grayscale noise, you will get a grayscale image out. So that leaves you with the color channels free for whatever you want to do with them. And one thing that you could do, for instance, is color additional properties. Use additional properties for color. Because one of the drawbacks of lick is that you don't see the gradient or the velocity. Okay, so whether the flow is fast or slow doesn't show up in the lick image. As a matter of fact, you usually normalize the input flow field to get uniform length traces. But even if you wouldn't normalize them, if your kernel is long enough, then generally you smear everything at least visually uniformly, so you don't see which direction the flow goes. So it's impossible to tell whether it goes this way or that way. Okay, and also you can tell how high the velocity is. So one way to recover that piece of information is to color code the velocity. However, color coding is not the most intuitive way of transmitting information. So it's much harder to interpret a color, in particular a shade of a color, right? Somewhere between, I don't know, in this case, red and green. In particular, if you're red-green blind, right? And it doesn't work at all. But you can choose other color maps. You can switch the color maps specifically for, I don't know, color blindness. But regardless of that issue, the problem remains that humans are pretty bad at determining where a certain hue is in between two colors, right? I mean, how fast is yellow here, or how fast is orange? It's really hard to tell. But it gives you an overview. It tells you, oh, here's a fast region, here's a slow region, kind of those things. And that's really what lick is about. It's an overview technique, right? So you use it to get a quick overview, and then you would look for parts of the flow that behave in a certain way. Maybe you're looking for vortices, maybe you're looking for laminar regions, maybe you're looking for regions with high velocity, or regions where the velocity changes significantly. But all of that you can see pretty quickly, and then you would dive in and you would use maybe another technique, maybe glyphs or particle traces, integral curves, to get more details. Okay? So that's the overall idea, and those are some of the additions that you can add to lick. Another interesting addition to lick is, in particular, to get rid of this this loss in direction information. You can do what's called OLIC, oriented lick. Okay. The idea of oriented lick is to use an asymmetric kernel. I mentioned, why would you use an asymmetric kernel? Now we're using one. For instance, if you use a kernel such as this one here, and that's very important, in combination with special noise. Notice that what I do here is I have an almost empty input image with just a bunch of random dots. If I combine that with the very same method, I just use this here as input, and I use this asymmetric kernel, then the result will look somewhat like this here. Okay, so I get particle traces again that have tails. Why do they have tails? Well, if it's an asymmetric kernel, that means towards the past of the particle, I use some of those values, but not into the future. Okay, so what we'll get is, for each particle, you'll see this trail where it accesses some of those white values that the line went through previously, but none of those into the future. So we get this asymmetric behavior then. There's an issue though with this method here, or with this extension, and that is, well, it's not dense, right? I mean, you recover the directional information, which might be very important, but you lose an important feature of the method itself, and that is its fact that it's very dense. Okay, why is it not? Why don't we see anything in some regions? Well, because we do traces through black, which results in, well, I guess black, right? So this is why we get a bunch of black points. Of course, you can put those white dots closer and closer together, but then you will converge towards the white image. So it does have its advantages and it does have its drawbacks. Another issue with oriented lick is its performance, because you do a lot of wasteful computations, right? All of those black pixels here in the image have undergone the same computation as the white one, right? I mean, we've all, for every black pixel, we computed those streamlines just to ultimately compute a weighted average over zeros, which results, well, in 0, so it's correct, but it's not necessarily the smartest way. The reason why this is still getting used is because it builds on top of existing code. So if you just implement lick once, if you want to get one of those images here once in a while, all you have to do is swap out noise and swap out your kernel, okay, which are really just 2 parameters or inputs. And that's the nice thing about lick is, while it doesn't produce images with the best performance, so just tracing the particles would of course be way faster, but you don't have to change anything. Right? There's this hammer-nail argument. If you have a hammer, everything looks like a nail. And here is this case, if you have this lick implemented once, you can just throw in a few other parameters and you're good to go. Okay, this oriented lick, and there's a couple of examples, a couple of additions to that. Again, you can make this a little bit faster, then you ultimately end up with something that my colleagues called FROLIC. Fast, I don't even know what the R stands for, oriented lick, fast rasterized oriented lick or something, but they just figured it's funny to call this after a brand of dog food. So anyways, that's one addition to lick that you can make. And here's another one that is lick on surfaces. So I've shown you this BMW image before, and I said, well, okay, I'll talk about how to do this on surfaces in a second. And here is the, well, I guess I said in a few minutes. We are here in a few minutes. So what can we do? Well, to compute lick on surfaces, you can simply project the surface into 2D and then compute lick. And that's pretty much the idea. So one way of approaching this problem would be, okay, we can assume we have our full 3-dimensional model. We take the flow field on that surface embedded in 3D. Right? We have some sort of parameterization. I mean, this must be output of the simulation or the measurement. So we know on the surface where is the flow field. So we have this sort of semi-3D data, right? I mean, we call this 2.5D data generally because it's on a surface, but that surface is embedded in 3D. So we take that 2.5D or 3D, whatever, flow field, and if we simply use 3-dimensional noise, we can just compute noise in a 3D array, and then ultimately get a 3-dimensional lick volume, but this one is only given at a certain surface point, and then we just simply render that. So we can assume that the lick is just the texture on the object. Could you use 2 colored asymmetric kernels which combine? Yes, you could, but I suppose that would be a giant mess in an image, because you would let's say I use red and green, right? I mean, which are 2 orthogonal channels. Let's say I trace red into the future and green into the past. So what you would get out is something that is, well, yellowish, because red and green are yellow. And in your mind, you would have to separate from the shades of color that you would get between red, green, and yellow, you would have to separate the parts that going one and in the other direction. Mathematically, absolutely no problem. Practically, I guess that would be a huge a leap to make that possible. Would require a lot of training. But we can just implement that and check what happens. I mean, I've never seen it, and I would imagine it doesn't work. But well, it'll create a nice and colorful image. So much is sure. Without blue though. Yeah, we could try this out. I mean, it's probably a nice thing to do in a late night coding session to fiddle around with these parameters. Since we have the code, we've developed it right a while ago. But yeah, that's one of the things. I mean, it's an interesting remark because it's one of those things where we would say, well, mathematically, okay, we choose two orthogonal properties and we just combine them. And of course, if it's just a linear combination, we can separate them out later, fine. Whether a human can do that, that's a different story. Okay, good. Now back to this one here. So that's one approach. Another much more efficient approach is to first project the vector field onto 2D. So you basically render an image of, say, the car or any other surface that has flow on it. So we basically just project whatever we see from the current view in image space, and then use that as input to just a normal Lick computation. Okay. Why is this much more efficient? Because it does the computation only in 2D, and only those visible pixels are computed. Okay. So it does have a significant drawback though, that since we project everything in 2D, we lose the 3D information. So let me just give you an example here. Say I have a flow field on a teapot. There are situations where, for instance, here the handle or the handle at the top, where nearby, okay, so here, for instance, well, let's take that one. I can easier point it. So here at the handle, right? So there are nearby pixels, this one and this one here, that have nothing to do with each other, right? So if I take this one here, that is in 3D relatively far away to that point because it's kind of in front of it, right? So I don't want any streamline to be computed across that silhouette. But if I first project the vectors into 2D, I lose this information. I lose this piece of information that there's two pixels nearby in the 2D projection. Then in 3D space, we're very far apart. And if I don't take care of that, I wouldn't be able to compute an image such as this one here, where the parts are cleanly separated. I would get strange transitions from one to the other. So how can that be solved? Well, the easiest solution to at least mitigate that problem is to keep the depth buffer around. So when we render the object into 2D space, when we render the projection, I usually use a depth buffer to resolve occlusion. And I can just simply keep those depth values around. And then when I do the computation of the streamline, I would terminate a streamline as soon as the depth buffer difference to the next cell reaches a certain threshold. So I would say, okay, well, if the depth is just, I don't know, different by 0.1, I assume that's just on the surface. And if it differs by 0.5 or more, that's a silhouette, and I just terminate the line. Okay? Just like any other epsilon, that's one of those typical epsilons, right? When do you decide whether you have a silhouette or not? Just like any other epsilon, this is prone to error. But for the usual scenarios, you can work this out pretty well. What you don't get out of this depth epsilon, though, is this type of transition here. Okay, so here where the handle is attached to the surface, the depth will be exactly the same. Right? I mean, that's what an intersection is all about, at the same point, right? So we wouldn't be able to detect that one. How did I figure that out and terminate the line? Well, I use a second epsilon here, and that's an epsilon, that's a normal epsilon. So instead of just writing out the vector field and the depth, I can also write out the normal. Obviously, I have normals computed here because I used shading, color, I used lighting as well. So apparently I do know the normals here. So what I can also do is I can take the normal along my streamline, and as soon as the angle between the normal also exceeds a certain epsilon, which it would do here, for instance, I also terminate the line. So again, there's a nasty epsilon in there that needs to be fine-tuned, and there's no really great choice for that one. But there's those are relatively easy to choose. So from my experiences, you can pick epsilons that are relatively stable, that don't create artifacts in one way or another. If you integrate these two things, a depth check and an epsilon check to the normal, you can catch internal and external silhouettes pretty well, and you can very efficiently compute a visualization of a 2D surface without having to do the full 3D computation. And again, this is usually only used as an overview technique, so if you want something specific, you would drill in anyhow. So I mentioned I do lighting and shading on this object here. So this is what happens if I don't do this. Okay, so this is again the BMW. It's a flow around a BMW car. And this is what happens if I just do what I said so far. So I compute the flow, I watch for silhouettes, internal and external silhouettes, and I color the object with the Lick result. Well, it certainly shows the flow field. It doesn't give me that depth, that structural information. So what you generally do is on top of that, you just compute lighting, diffuse lighting, and you simply multiply the object with that diffuse lighting value. Okay? So this will give you this depth perception back. It'll result in that structural perception. You could also add shadows if you want to. I didn't add shadows here because I didn't want to make it too complicated, but if you just do shading, you already get a lot of the structural information back. However, there's one issue, and that is we're now using the same channel for two different pieces of information. We're using grayscale, which is just one channel. We use that to convey A, the flow behavior, and B, the structural behavior. And that could cause problems. Not that the brightness values in Lick have any meaning, right? Whether a line here is white or whether it's black or bright or dark, does have absolutely no meaning. That's an artifact from the noise, right? If I vary the underlying noise, this dark region here might well become something bright. That's an important thing to remember. The color or the brightness itself has absolutely no meaning in Lick. The only thing that has a meaning is the structure of the color or brightness. Okay, but nonetheless, we're using one and the same thing for two pieces of information, and that can be especially bad in situations where, for instance, our lighting tells us this part's supposed to be black. If I multiply anything with 0, it's going to be 0, so I don't see anything. So how can we not use the same channel to convey information? And well, we still have color, right? So what we can do is we can simply take that lighting information, that brightness information that we get out of the lighting computation between 0 and 1, and use that to modulate the grayscale values between two extremes. For instance, use cool to warm shading, as it's called, and that generally implies that you use a color gradient from blue to, say, yellow in this case here. Okay? This way, the brightness is still solely used for the Lick computation, and we simply use the color information to transfer structural information. In this way, there's the worst thing that can happen if something is completely dark, in this case it would be blue, and something completely bright, it would be yellow, but nonetheless, still, we can perceive the flow. And there's no reason why we shouldn't invert that, right? We could also use color information for Lick, right? We can map that 0, 1 to, say, cool to warm, and we could use brightness for the other channel. Okay, so in that case, we would probably add the two to avoid getting those 0 values. So you can do all of these things, and it's kind of up to personal preference, I guess, which one works best. Okay? But bottom line is you have to do a little bit on top of the just 2D projection Lick computation to visualize the three-dimensional structure. Talking about three-dimensional structure, what's full 3D? I mean, we talked about volumes quite a lot. What if our flow field is a volume? Now, there's an issue with Lick that I mentioned before, and that is the values itself, or the values themselves, right? The values between white and black do not have any meaning at all. They're just artifacts from noise. The only thing that carries information is structure, is homogeneity. Yeah? So if there's something homogeneous, we know, or our brains interpret it as a line. The line doesn't really exist. It's not a white line, it's not a black line, it's just some consistent, coherent behavior of nearby pixels. And that causes an issue when you want to lift this to full 3D. Why? Because, well, the output, while we can run Lick fine on a volume, right? I mean, Lick proceeds with each pixel separately. So instead of running it on a 2D array, we can easily run it on a 3D array. There's no complexity involved with that whatsoever, except that we need a third loop in our code. But that's pretty much it. And the result is a volume. However, this volume is going to be a black and white or shades of gray volume. And we can visualize that, but we can't look really inside. We would have to use clip planes, and then we might as well compute 2D planes to start with. So the problem is it's opaque. We don't have a notion of transparency. We could map the brightness to transparency, right? We could make white lines more opaque or less opaque, I don't know which direction you prefer, than dark lines. But again, the trouble is the color itself doesn't carry any information. So, but we need to get the volume to be sparse enough so that we can look inside and see the interior. And that's the next problem. We don't want the volume to be sparse. I mean, that was the whole point to start with. It should be dense. Okay, so there are extensions to 3D. So here are a couple of examples of 3D Lick. And on the next page, you see what happens. So if I would just compute Lick in 3D, I would get this one here. I would get an opaque volume, and here it was color-coded to make it at least a little bit easier to perceive. And in this case, I think it's the magnitude that was mapped to a rainbow color map. So, but what you don't see is all the interior, because all you get is a, well, now colored, but still black and white shades of gray image. So if you want to see the interior, you have to use some sort of a sparse noise. For instance, remember, oriented Lick, I could use a very a generally black volume as noise input, and then just have a few points that are white, and then I could say, okay, well, now the color actually makes some sense because I could map almost everything to transparent, all the dark values, and just the white ones, I map those to a few opaque points, and then you can see the inside. You can also add other smart ideas, such as using the gradient to vary your kernel length or vary the transparency. So there are some other additions, but for me, the bottom line is Lick does not work in 3D. Okay, why? Because you can make it work, but you basically turn it into a bunch of particle traces, and you might want to compute the particle traces to start with, because again, it would be way more efficient instead of computing all that empty space here through some convolution operator. Okay, so while yes, you can technically tweak it so that you get some information out, but I don't think it's worth it. Okay, why? Because it's inefficient to compute with, and to start with, the computation is inefficient, and you ultimately need to volume render the whole thing, right? I mean, you can use the things that I explained so far for volume rendering, slicing, for instance, or ray casting, but that is also very costly. It's way more costly than just computing a few thousand particle traces and then using simply geometric lines to render those traces. So again, it's this hammer and nail kind of thing. Yes, you can use your Lick code and you can use your volume rendering code both together, and you can do 3D Lick if you use an appropriate kernel and appropriate input noise. But it's going to be dead slow compared to just rendering maybe a few million lines. Okay? But nonetheless, it does work, or not. I would say it doesn't work. And it's not very popular. So I've seen a bunch of publications on that one, maybe about 20 years ago, but then they kind of stopped because it seems like no one really picked that up. So that's pretty much all there is to know to Lick, almost. So little anecdote here. When I was a student a couple of years ago, well, a couple of decades ago now, oh, I'm old. Okay, when I was a student a couple of decades ago, that was pretty much where a Lick lecture would stop. And I checked colleagues, web page visualization colleagues, nodes, and then sometimes, like, we talk to each other, professors talk to each other, and we steal or we copy, we replicate nice slides from other colleagues as well. So what I noticed is that almost all introductions to LIC stop at this point here. Maybe before the 3D LIC, because I guess most people agree that it sucks. But anyways, it stops here. Okay, and and the same happened to me a couple of decades ago. So I went. I didn't have an exercise to go with the visualization lecture, so I simply implemented it myself. So I simply, okay, figure, well, that's easy. Let's just do it. I mean, it's basically a 1 hour, 2 hour job to get 2D LIC together. If you have if you have decent programming background, and the result was terrible. So the result was for a flow field, if I spent hours and hours after I got the actual implementation to work, tuning parameters, which I said there aren't any, but I'll tell you in a second there are some. I tweaked parameters. I got something like this here out, right? It's a shabby grayish image, and all I saw in the lecture were images such as this one here for the same flow field. Okay, so I figured I must be doing something wrong. So I spent literally forever trying to debug the thing, and I realized no, there's nothing wrong, and it's actually and there isn't anything wrong except that hardly anyone bothers to explain the full story. Okay, because again, what I explained so far will give you garbage such as this one here. Or it's not complete garbage, but it looks not very. It doesn't look very nice. I mean, nice or not nice is not generally a visualization parameter, but you certainly see less of the flow than you do on the right image. And that's actually something that I spent a lot of time optimizing parameters on. So what are the issues with LIC? And there aren't really any issues with LIC, so it's just that people only explain half of it. So why do I get such a gray image? And what are those parameters that I talked about? Well, the first parameter is how far do I go for these traces, right? Remember I said we start for each pixel, and when we go a bunch of points, maybe 100, right? I literally said maybe 100 in one direction and 100 in the other direction, right? But where does that 100 come from? I mean, it's kind of an arbitrary choice, right? Why don't I do 200? Well, it probably takes longer. Why don't I do 10 then? It's 10 times faster than 100. So what's the issue with that? Well, let's try out a little bit of theory here. So what happens if I do a very short kernel? Let's take the extreme case. Let's say I do 0 steps. Or 0 steps in one direction and 0 steps in the other direction, which basically means take the center. Okay, so the result will be, well, the input noise image, because I don't use the flow field at all, right? I just do a very silly computation that says for each point, just grab the point, right? So the output is the input, obviously, then. So I get noise. That's probably not a good idea. Now let's take this to the extreme case and do a very, very long trace. Let's say 10,000 points in one direction and 10,000 points in the other direction, giving me roughly, or exactly, 20,000, and I guess in one, if I take the center into account, point. So a bunch of points, 20,000 points roughly, okay? So now let's do the theory here. So what do I take as input noise? Values between 0 and 1. So, and I mean, there's nothing wrong with using uniformly distributed values. So I have values that are uniformly distributed between 0 and 1. And now imagine what happens if I take 20,000 values between 0 and 1 and compute an average, either weighted or non-weighted average, doesn't matter over those. I'll get a pretty decent approximation of the expected value, which is for uniform distributed numbers 0.5, right? So if you do a long kernel, you just get 0.5, you just get a medium gray image. And you can, I mean, if you participate in the exercise, take the code, make the kernel long, you get exactly that. It takes forever to compute and you get just medium gray out. And that's what I spent a while on, is trying to find a kernel length that would, well, give me not noise and not gray, but something in between. And that's exactly what you get. You get something in between noise and gray. And the next nasty thing is, what do you do with all those lines that end up, right, that leave the domain? I mean, you can only terminate them. There's nothing you can do. right? So you get artifacts at the places where you either leave or enter the domain, because you have shorter kernels, so you'll observe more noise here than you have here. So in other words, while the technique basically works, I mean, I can see this flow field, this curvy field around that critical point in the center, it also basically sucks in terms of visual quality. So how do we get to this point here? And let me show you a sequence of images here. So that's the original one, more noise, less noise, smoother, blah, blah, blah. So somehow you can do something with those images to make them somewhat better looking. And better, again, I don't mean it looks nicer. I mean, it also looks nicer, but it also transforms the information, translate the information better. And that's a very low resolution image here. So you can actually see the single pixel, but still it's smooth. It's still kind of sufficiently smooth. It's not grayish, nothing. So how does that work? Okay, and it involves two steps basically. So the first one is to get away from that center noise value, which you will always converge towards, right? If you use longer kernels, you'll always end up squeezing your values around your expected value, around your 0.5 for uniformly distributed noise. And one way to get away from such a distribution, so here's an image, right? That's an image that is pretty close to some value, some well, it's probably around 0.5, but at least I'm not using the full value range. And that's what you can see here in the histogram. So histogram, talked about that a few streams ago, quick repetition. Histogram is basically a bar chart, at least the visualization thereof. It's a count, how often does one pixel value show up? So we see no white values here, no very bright values, a couple of those, a ton of gray values, and then no black values either. All right, that's a bar chart. So this is the histogram here. What you see the black curve here, that's the cumulative density function, or CDF. And that's basically just the sum over the red one. So from left to right, we sum the red one up. So it starts at 0 because, well, we have no pixels for most of the low values here. Whoops. Okay, so we've got a bunch of zeros here. And then we sum all those red bars up, and we end up with 1 in the end, right? So this is a normalized curve, so this is 100% and 0%, so to say. This is a so-called CDF. And there's a method called histogram equalization, and that's basically what you get if you use any of your favorite image processing software, and you click this button like optimize, right? Then histogram equalization runs. So that's optimize. It's just a, I don't know, human readable name, or enhance, improve quality. It's got a bunch of fancy names, and it's always the same basic thing. So the software just does histogram equalization. So if I run histogram equalization, and I tell you in a second how this works, on that image here, I get the image on the right out, and I get this histogram out. And in particular, I get this CDF function out, which is almost a straight line, except that it's a little bit staircasey. But that's basically what we want. So why is that what we want? Because if we spread out our histogram over the entire range, right, and see how it's kind of spread out, so it's actually the same bars, right? Notice that these bars that you see here are exactly the same bars as here. It's kind of hard to see. I mean, admittedly, they're small, but I just spread the bars out. I can't take any of the bar and split it up, right? Because what does a bar mean? Like, one of those bar means, okay, how many pixels are, I don't know, 0.6. And I can't just say, well, make half of the pixels brighter and half of the pixels darker. That doesn't make any sense, right? Because I don't know which pixels should I make darker or brighter. This is just a sum of all the pixels. So all I can do is say, okay, all the pixels that are 0.6, make them 0.4, right? And that would just shift this thing around. So the bars are the same. They're just close together here, and here they're spread out. Okay. So that's the red thing. Now, why are we striving to get the cumulative density function to look like a straight line? What's the rationale behind that? And the rationale is, well, if that thing is a straight line, it means that, well, when we sum values up here, we always roughly sum up the same amount of values, otherwise we wouldn't get a straight line. That means we have about, for each brightness, roughly, if it was a perfect straight line, and exactly, if it's like a wiggly straight line, we get roughly the same amount of bright, medium, and dark pixels. Like every shade of gray appears about the same, which means we make best use of our value range. Okay, so that's what we're trying to get at. And we get an image that is spread out, that has much more contrast than the original image while still retaining the structure. You wouldn't retain the structure if we take half of those images and put them, half of those bars and put them anywhere else. Okay, so how is that computed? And it's actually pretty simple to compute the histogram equalization. First, we compute the histogram, and then we compute from the histogram a few values. CDF min is the minimum value where this combinative density function is non-zero. Okay, at random. Could you add random noise? Well, you could, but why would you want to add random noise to your photograph, for instance, or other image, right? I mean, that would destroy the lick computation. Talking about lick, right? If you add noise to it, you would simply destroy your smoothing that you did before. So get back to this. What's CDF min? CDF min is the minimum value where this function is non-zero. So that's, or in other words, that's the first entry here that has a non-zero value that has some chart. So this, I guess that has some bar chart, some red bar chart. So I guess that would be about here in my example. Okay, so the first thing we do is we subtract CDF min, which is say grayscale 0.5, right? So that's the point. That's the point where the cumulative density function becomes non-zero first. So and that point is maybe here 0.5, right? About halfway through the through our range. So we first subtract that. So that will basically shift everything to the left. So we start at 0. So you can also see this here. Forget about this multiplication for a second. Okay, so we simply subtract CDF min. And now we compute a quotient of two values here. And what is this? This is the current CDF divided by width times height. What is width times height? Well, width times height is simply the number of pixels. Okay, so if we compute CDF not as a normalized function, but as a function of pixels so far, this is the value, this is 1, right? So this is the value the CDF will have in the upper right corner. Okay, so what this basically does here is it tells you, well, the overall pixels so far divided by the total number of pixels. So this is just a normalization. Okay, and this is what I multiply each position with. So if I'm here somewhere in space, okay, so if I'm at this bar here, I want this bar to be where its height matches its position in xy, right? Because if its height or the accumulated height so far matches the position, then I would get this line here, right? Because what is a diagonal line? It says at value 5, I want to get height 5, okay? So I simply take every value and shift it to the position, right? I mean, I first shift everything to the left. And then from there, I shift it to the position where its position is equal to the cumulative height so far. Okay, and the cumulative height is the number of pixels that I've accumulated so far divided by the total number of pixels. And that will give me a value between 0, 1. And since my range isn't 0, 1 here, it's just, I don't know, between 0 and 255. I'll multiply it with the number of values that I have, which would be 256 minus 1, right? It's just 255 as a maximum value. And since colors are generally integers, right? 8-bit, for instance, we round the result. Okay, but this is really it. So it's a very simple idea. Shift everything to the left and then make the steps from one value to the other as big as the cumulative density function that we've accumulated so far. So it's a pretty straightforward computation. So what this will do is it'll spread out, well, that's how it's designed, it'll spread out the values to the entire range. So if you run lick on with a significantly long kernel, you will get something that is almost gray, but it has these tiny variations in there. Say I compute this in floating point or double precision, right? I use pretty high precision. So I computed mostly gray values, but they still have a little bit of noise in them, right? Depending on how long I made that kernel, the longer I make this kernel, the smaller the noise is. But I still have some random deviation from the mean, right? So that said, I get everything squeezed into this tiny range around, say, 0.5 around my mean, but if I do histogram equalization, I spread it back out. Okay, so with that, let's just go back here. We turn this one into that one. Okay, now I take these tiny variations and I spread them out. Well, that still doesn't look like this one here, right? I mean, because now we take this residual noise and we blow this residual noise up again, right? I mean, it does have much more contrast. I give it that much, which is obvious because we maximize the contrast here, but it's again pretty noisy. So any tiny variation here along that line will again be blown up. So how do we fix that part? And that's kind of an interesting idea. It's like, okay, what would we like to do? And in case someone attended the lecture before late night coding, please don't spoil my joke here, okay? What do we need to do? Well, to get from here, right? I mean, this is LIC, right? This is input computing LIC. This is histogram equalization on top of that LIC. And now, how do I get to this point here, right? What I would have to do to get from this image here to the next one, I would have to, well, obviously filter the noise out, right? I mean, I don't want the noise in there. I mean, it's just something that I use to create this uncorrelated behavior across a line, but I'm not interested in the input noise, right? I mean, it's obviously noise, and that's generally not a very good idea. So how do I get rid of that? How do I get rid of this noise? And how do you generally get rid of high frequencies in a data set? You filter it, right? I mean, you use, like, if you have noise in any signal, you run a filter that appropriately catches that noise. Say the noise is high frequency, then you run a low pass filter that just boosts low frequency, such as simple averaging, right? So if you just have noise value, for instance, you average your signal, and then, well, noise is gone, and hopefully not too much of the signal is gone either. So what we would need is some sort of technique that filters this out, but does this in a very specific way. I don't want to just smooth this entire image out. That doesn't help, right? It will just create a smoothed out, washed out image. I want this smoothing to be somewhat, well, I would say specific, right? I want this image to be smoothed out, not across the flow, right? I don't want to compute a smoothing between this dark value and here, this bright one. That's cool. I mean, it's good that this is dark and this is bright because I can distinguish the two traces, right? I want this one to remain as it is, but I want to get the noise out along one of those traces, right? And those are curves, right? It's not straight, right? So I want a method, I want an algorithm that selectively smoothes this image out in the direction of those lines, which is the flow, right? So we have to develop a method that selectively smoothes out this result of a LIC computation followed by a histogram equalization step so that it filters the noise along the flow. So any ideas what this method would look like or how this would possibly work? I get something to drink in the meantime. I'm outside bag. So it's a little bit early though, all right? Should be 12. So does anyone have a clue how this selective smoothing method could work? Or if it's something that I talked about maybe before in any of the previous lectures. Okay, that is not much. Okay, but this is not not unusual. So this is what I've seen the last couple of decades when I present this. Well, you know how it works. So what should I do? I need a selective smoothing along the flow, which will give me this result here. So what is LIC? Well, LIC is selective smoothing along the flow. Okay, I mean, what does LIC do? I mean, it smoothes values along the flow, right? So all I do from this image here to that image is I run LIC again and use as input not the noise, but use as input the previous result. And then I run histogram equalization on that again, run LIC on that again, run histogram equalization on that again, run LIC on that again, run another histogram equalization. As you see, this whole thing converges, right? lesser and lesser changes happen. Lick again, histogram equalization again, just boost the brightness, and we're done. So the simple idea is just to iteratively repeat the process. Do lick, histogram equalization, rake, histogram equalization, and voila, you're done. So it's a pretty simple process, but it's a very important step. And then if you do this, all of your things such as kernel length and so they basically lose their importance. I mean, you still need to use a decent kernel, right? I mean 50 steps or so, not just 1 or 0. Right? That would not give you anything. But as soon as you use some reasonable amount of steps, if you use too many, doesn't matter, histogram equalization, if you have enough precision, will capture that back. It probably takes longer, but that's pretty much it. If you use too few, well, you just end up having to do more of those iterations. If you do this to some convergence property that you can choose, well, maybe you don't want the images to change by more than 1%. It's very stable with regard to the input parameters. Okay, so that's a pretty simple thing. So all you really need to do is, let's get back here, is to repeat the process a couple of times. Okay. However, say we care a little bit about performance, right? Say we don't want to just run this until convergence with some silly input parameters. So maybe we can choose those parameters, that kernel length thing, and also the number of iterations, so that we get nice quality. I would say that's probably, for me, this one's the best here. We get nice quality at a pretty fast rate. And who says that lick histogram equalization is a nice idea? Maybe you want to do lick histogram equalization, well, 2 histogram equalization after each other don't make any sense, but maybe you first want to do 2 lick passes and then a histogram equalization. Okay, how should we ever know? Well, it turns out the original publication from a couple of decades ago actually recommends this idea, right? And that's what a lot of the colleagues never mention. I don't know why they skipped that part, but it's actually in the original publication that says, okay, you want to do this lick first, and then histogram equalization, and then lick again. And they have this kind of hand wavy thing where they say, well, it's like lick histogram works fine. You don't need to do more passes. And the question is why? So what you can also do is you can mix multiple lick passes and then do more or less of those histogram equalization steps. And you get multiple results. So I would say overall, all these results are kind of reasonable, right? But that has more noise in it. This one's smoother here. That one's got, well, I don't know, some more noise in here. And that one just has shorter structures. And what's interesting is that different people prefer different visualizations. So again, for me, this one here is probably the best, but there's no uniform truth to that. So some people say this one's, I think that one's better, or this one's better, or I don't want these small scale structures. Here's our example from before, because they give me headaches, right? I mean, it starts to flicker, and it's probably dependent on your eyesight, maybe on the screen resolution. So I'd rather have this not so extreme a zebra type of image. I'd rather want this a little bit more towards grayscale. So bottom line is, depending on your sequence of execution and depending a little bit on your kernel length, you get more or less noise, you get longer, shorter traces, you get more zebra or more gray. And surveys have shown that there's no optimum case here. It's really user dependent. Okay, so some people prefer one over the other. And that's bad, because it means we somehow have to adjust the visualization to a user. And there's 2 ways to approach this. One is to, well, give the users, give them handles and knobs. Right? Literally, let them tweak the parameters so that they like them, right? Kernel length, number of iterations, sequence, whether you want to do lick, histogram, whatever. Right? Give knobs. Knobs and dials, as I said before, are a source of error. So maybe not such a great idea. Right? And then there's overall this question like, when should we terminate? So another approach is, can we make a computer system do this automatically, figure out what's the person's preference, and then somehow work this into the visualization. For that, first of all, we need to understand the quality of an image, right? Or the computer needs to understand the quality of such a Lick image. Okay, so here's a Lick image. Let's look at a small part, right? So that we get a better view. So this here is this is the small part of this image here. Now, if we say for a second we want to be as ZBrush as possible, okay? So which means we have basically black, white, black, white, black, white stripes, right? From purely coherence and non-coherence point of view, coherence along the line, no coherence across the line, this would maximize it, right? So if I have white and black lines alternatingly, we have absolutely zero coherence from one line to the other. One is one extreme, the other is the other extreme, so they uncorrelated. And we have a white line which is perfectly correlated, and a black line as well, a gray also technically. So what we could do is we could measure that, right? We could take a single point here, take that single point here, and we look at the vector field direction. Okay, so we take the output of Lick and we take the input flow field. And here, say the input flow field points that direction. Now I compare that to the image gradient. And what I would like the image gradient to be is perpendicular to that flow, right? Along the flow, I would like no change, and across it, I want to have maximum change. So what I want for a zebra style image, so I want this image gradient to be perpendicular to the flow everywhere. Okay, now I can compute the image gradient and check, is it perpendicular to the flow? Okay, so this here is the perpendicular vector, and this here is my image, wait a second. This here is my image gradient, and the green one is the perpendicular vector. Now, as you can see, the image gradient isn't perfect, right? I mean, it's not exactly perpendicular. It's pretty perpendicular, right? The blue one is pretty well aligned with the green one, but there's a little bit of a parallel component, which I colored red here, right? I need this component plus that one to get this blue component out. So now what I did is I assigned to every pixel a red, which I say bad, and a green value, good. Okay, now I can just show this. This here is what happens if you do that computation on the entire image, and you just color the red and green values. Okay, so you see some places are green, some places are red, some places are yellow, which means they have a red and green component, and some are black. Why? Because I added, because I basically overlaid that to the original Lick image. And then at some places that are generally uniform, this gradient is very small, right? How long took that red-green posting for you? What do you mean coding? To code that up? I mean, that's trivial, right? I mean, this is something that I know, 10 minutes or so. Just do dot product of the image gradient with the flow field at that point. So that's fairly straightforward. So what you see are these places. So now what can we tell from those images? Well, two things. First of all, green regions are good, red regions are bad, but dark regions are also bad. Why is that? Well, in regions where we have no gradient at all, right, where through some random coincidence, everything was smooth, right? I mean, if you throw random noise at Lick and let it compute, there's some probability that the whole region will be, I'd say, in the input noise will just be black pixels, right? Any line that runs through those black pixels will also be black, right? So in that region, we don't have an image gradient or a very small image gradient only. If I compute the red and green components and I don't normalize them, if I compute the red-green components now, they'll be small. So red will be small, green will be small. But that is also bad because I don't see anything at all in there, right? I mean, what I want is high green values with no red values, so to say. Okay, so that's kind of what you would expect to get as a result. Now let's check parameter settings. Okay, let's check what happens if I run my Lick with different parameters. So here you see the same flow field. It's the same flow field computed with two different parameter sets. And on the right, you see these red-green images. Okay, so what I used at the top was a fairly long kernel, right? A relatively long kernel. And that creates very smooth images after a few like histogram equalization and so on iterations. Okay, so that's good. So here I used a very, very small kernel, and what this creates are well small snippets of lines, obviously, because the correlation is smaller. Right, even after a few iterations. I mean, if I do more and more lick iteration, those kernels will get longer, but I mean, I terminate at some point. So this here, certainly, here you can see the nice laminar flow around the cylinder. And here, well, it's a little bit messy. But now comes the nasty part. In the turbulent region, our long kernels produce very bad results, because what happens, well, my long kernels, they run into critical points, into vortices, and they kind of spin, and use the same values all over again. So we get large uniform blobs. Okay, so here apparently in the middle of a vortex, there's a white pixel in the input noise. So I can iterate over that white pixel for a while, and I get large white blobs. With shorter kernels, well, I don't do so many iterations in my critical point, so I see more here. Okay, so if I observe this here in my red-green image, you see there's more there's more green at the top. So if you compute the overall green pixel sum, you will get a better value there. You have more red here, and you also have more darker regions here. But in those turbulent parts, we get better results here, because here we get large black spots, which are also zeros. So now what you can try to do is you could try to combine this image into a single metric, into a single number. Okay, so this here is kind of the result of the single number, the function here. So what is this all about? Well, it takes the black and the red component, and this here is that's parallel. That's the red component, right? This is how much of this vector is parallel to the flow, right? And this here, whoops, and this here is the green component. Okay, so you can say the quality of an image is the sum over all pixels of the red ones minus the green ones. Okay, and there's this factor of lambda here. There's a normalization that's divided through all pixels, just to normalize that. And there's this weird lambda in here, right? How much do we weight the red ones, the green ones against the red ones? And this lambda here is something that we've chosen to be 0.26. And where does that number come from? That comes from a user study. So it's like, okay, which one do you prefer? Do you rather want these images that are more zebra-ish, or less zebra-ish but are somewhat smoother? And it turns out that the result of the user study was that 0.26 is for all users the optimum value, but it's actually the distribution is interesting. So we saw that 0.26 is kind of in the center, but it's a binormal distribution. So there's a couple of people that prefer a significantly lower number, and some prefer a significantly higher number. So 0.25 to 6 doesn't really tell the whole story. So you basically want to pick between one of those two numbers. Apparently, there's these two classes of scientists that we've observed. But that's just one parameter that you can either say that one or that one. You could technically just ask a user upfront with a bunch of well-known examples, which one would you prefer, and then pick that number. Okay, but this allows us, once we figure out that number for a specific person, or we just use the generally centered number, once we figure that out, this allows us to judge the quality of an image automatically. That's the key point here. If we know what is a good image, if the computer knows what is a good image, you can run your iterations until you get a small value, until your M, which is your error, your quality metric, or if you get a large one, M here in this case grows with quality. So until you get a significantly high quality. And what's even better, you can do surveys. You can basically run different parameter sets. You can just vary the kernel length. You can just run for hours and hours. You can check all kinds of lick, histogram equalization, like these sequences to figure out which one is the best. Okay, yeah, you generally have just one parameter to choose from, but that seems to be constant per user. So it's kind of a thing that you do once when you install the application, like which image do you prefer? And then all parameters are gone. So what you can also do is check out what's the optimum sequence of licks where this histogram equalizations, and you can do this over literally thousands of, or millions and millions to be precise, of different sequences of Lick and histogram equalization. And what turned out, which I found very funny, when a while ago we did those tests, it turned out that the sequence of Licks and histogram equalizations proposed in the original paper was almost optimal. So you could do, I think you could do one more Lick step, and then that was optimal with regard to any lambda. The lambda really only determines the kernel length. But it was pretty nice that kind of a quick shot, a guess from colleagues a few decades ago turned out to be, if you actually survey over millions and millions of setups, it turned out to be pretty close to the optimal. Okay, and here are just a few examples. If you throw this into an optimizer, like optimize towards a certain lambda, this is what you get. So those are certain intermediate results, and then here is the final result that the system then found automatically without any user intervention or knobs or dials to rotate with. You see something that is almost exclusively green. So there's some red points here at the boundary, but boundaries are a special topic. But overall, it's almost green, and there's and also the black parts are minimized. Okay, so that's one approach to get rid of the parameters and produce an optimal image, maybe per person. What you could also do is you could take this one step further and do this parameter optimization not per image, but you can also optimize this per pixel. Coming back to my example of this flow around the cylinder, right? So there were some regions where you would potentially prefer shorter kernel length over a longer kernel length somewhere else. And you can also do this optimization per pixel. It just takes significantly longer to produce one consistent image. Okay? Since it's now a computer parameter, you don't care how much computation this costs. Well, you don't want to wait forever, but you don't have to tweak the parameters yourself, which would be almost impossible for a human to tweak per pixel parameters. At least at that point, it gets ridiculously complicated. Okay, so that said, there's one other thing to notice, and that is, well, with all this trouble we go through with Lick, histogram equalization, and so on, we try to enforce one thing sort of implicitly, and that is on top of the high correlation along a line, we want low correlation across it. But we basically let this randomly happen, right? The low correlation across the flow is something that we just hope and pray will ultimately come from the noise, but we never really enforce that, right? So there's nothing that takes care of that, except the fact that it's, well, if the noise is noisy enough, it'll happen automatically. So what you can also do is, you could just enforce that literally. You take a high-pass filter. So our Gaussian filter is a low-pass filter. You can take a high-pass filter and filter that across the flow. So you add another stage, you have Lick, you have your histogram equalization. You can do something that we call perpendicular Lick. So basically you rotate the vectors by 90 degrees and also filter them with a high-pass filter. And a 1D Gabor filter, for instance, is something that you can use. This is what it looks like. If you're interested in the detail, check out Gabor filters. But the bottom line is, it's just a filter that boosts high frequencies. Right? In particular, Gabor filters are perceptually motivated, but that boosts high frequencies. So with such a filter, we can, instead of just hoping that things will differ sooner or later, we can just make them, we can increase their differences. Okay, so, and with that, like perpendicular Lick filter or whatever you want to call it, it's really the same application. It runs the same code as Lick, except that you swap out the filter and you rotate every vector by 90 degrees. If you do that, after just a few iterations, you converge towards an actual zebra image. So you can enforce this as much as you want. And again, how much zebra-ishness, I guess, you prefer in your image is very personal, is a very personal choice. And again, I think it depends. So my guess is, without having ever specifically researched that, my guess is it depends on eyesight. Well, yeah, as I said, you can adjust that to your needs. Yeah, so you can do this pretty fast. So if you run this on a graphics card, this computation, since it's independent for every pixel, can run very fast. It can run at interactive rates, yeah. If you don't do too many iterations, which you don't need to. Another interesting side note, anecdote about this application here is that there's one thing that you still need for a lick, which is a little bit annoying, and that's the input noise. Okay, because well, it produces noise, and it creates these nasty things that your noise can maybe be very uniform at places, right? I mean, there's some chance you can tweak your noise so that it avoids uniform places, but nonetheless, there's still this noise input in there. And one of the funny things that we figured out when we do this perpendicular filtering is that you can actually start with no noise at all. So you just start with uniform values. And if you run this computation with long filters in floating point precision, you'll start to accumulate noise just from adding and dividing values. So if you run this at the limits of floating point precision, like doing long kernels and doing ridiculously long iterations counts, like literally thousands of iterations. Not that I would recommend this, but it's just kind of a funny thing. You don't need input noise, right? Because your computation will accumulate noise just from the floating point inaccuracies along the way, that at some point, like as I said, after a ton of iterations, you'll have some variations, local variation, and those will spread out over the entire domain. So you can literally start, if you use very long kernels and a ton of iterations, you can literally start with no noise at all and just use uniform input. That does work. So you can technically remove that parameter and just use the noise that's already in your computation as input. Not that this makes a lot of sense, but it was kind of a funny observation. Okay, so with that you can boost the contrast to very extreme levels, and again, it's very personal whether those extreme levels are actually preferred or not. Finally, one last thing before we're done with lick. I just want to mention it. What I talked about was lick, straightforward. 3 lick, which I think doesn't work very well. Various methods to, first of all, get it to work, and then some automated methods to improve the quality. But what is with time-dependent fields, right? What is with fields that are flow fields that actually change over time? And here you see an animation of a lick computation of a time-varying flow field. So it's a flow around, it's so-called Kalman vortex street. It's a flow around an object. And what we did here is we computed streamlines in every time step, computed lick image, and then created an animation of those streamlines, which is kind of you need to know how to interpret this, right? It's not a path line, so it's not actual flow, but it's a sequence of streamlines. Okay, so scientists know how to work with that, but it might be a little bit counterintuitive. Okay. What's another interesting property that you see here, if you go to this very extreme level where you have like literally zebra image, you see a bunch of like grayish spots here, right? And that is whenever 2 lines get very close together. Again, they never cross. I mean, that's a property of streamline. They can never cross, and they cannot merge, but they can get very close together until they are so close together that they're actually subpixel. The difference is subpixel, and that will visually create a merging area. And at that point, of course, your zebra has to break down because, well, you have to make a choice, right? If a black and a white line kind of combines into 1 pixel, even though they're still separated, but the distance is subpixel, right? You have to those places have to be in the visualization, and those again might be somewhat distracting, right? Because it looks like random spots, and the position actually of these spots is pretty much random. It depends on the computation. So that's another argument why you want some blur, some gray in there, so that these things are not visible. Because again, the exact position of these points where 2 of those lines happen to be subpixel in distance is arbitrary. Nonetheless, with some additional trickery to make the images time consistent and not flicker over time, takes yet a few tricks to get this to be consistent over time that I don't want to mention here because it's a lot of engineering. involved. But anyways, with that, you can, shut up, you can produce also time sequences, okay? At least for streamlines. Path lines are a little bit tricky because path lines can actually overlap, and that would destroy some of the properties of Lick. So streamlines are the choice to go, or same as for streaklines. Streaklines can also overlap, or at least their 2D projection in the 3D time space. If you look at the 2D projection, they can intersect, and that would create issues here. Okay, well, that's pretty much it for Lick. As I just heard, that's also from a timing point of view perfect. So we're done for today. So what's left in visualization, scientific visualization this term, are topological methods. So we'll spend the rest of this semester. I think we got 2 weeks or 2 sessions remaining. So we just started. I think we're 3 more weeks, including this one. So we got 2 sessions remaining, and I want to talk about topological method, and maybe at the end have a Q&A depending on how quick I am with the topological method. And this just to give you brief input. So that's a flow visualization using topological method. So it's going to be another one of those fun visualization things that certainly requires some expert knowledge to analyze why that is a flow field and what those little balls, lines, and everything have to do with flow. Okay, so that's it for today, unless there are any questions about today's talk. So it doesn't seem to be the case. Then, as usual, feel free to ask questions on Moodle or in the exercises if you are a student of the University of Duisburg-Essen. Participate in the exercises. It's good training, and I don't know the BMW, but that's ancient, right? I just know at the Turing it was like a how do we call them, combi, right? But it's very old data. Generally from the industry, you only get ancient data, right? Because they're very picky about their modern data and somewhat stealing the results. So it's a very old data set. It's maybe 30 years old or so. It's probably a 5, yeah. But it could be a 3. It's certainly not a 7 series. Okay, anyways, that's it for today. We'll have late night coding coming up tonight, and we have more advanced image synthesis this week, and then next week we'll have topological methods, and we'll see what those things can do for us to understand flow better. Until then, as usual, if you can get your vaccination, to stay healthy, and I see you again, or you see me. Bye-bye.